Welcome back, everyone, after the coffee break. So, next speaker of the day is Zoe Chatzidakis, and I do apologize if I did not pronounce the name correctly, from Paris. And Zoe will be talking about an invariant for difference field extensions.
Thank you. And first of all, I would like to apologize for the mix-up I had about a month ago when I just totally forgot about the seminar. I'm really sorry about this. This does not happen to me. I guess it was excitement about getting an appointment to get vaccinated and sort of wiped out everything from my mind. I mean, just I forgot about everything. Okay. So sorry, I hope that the talk will go well. So the title is a bit misleading because, okay, this new invariant was new about 10 years ago. Actually, now it's not new anymore. But, well, let's say that it was not an invariant which was classically considered for difference fields. So let me show you the references. So it's a paper, it's a joint work with Hrushovski, with whom I've worked quite a lot on difference fields, actually. And the geometry of their definable sets, I mean, of sets defined by difference equations and stuff like this. And so we had quite a lot of results on it, on the problem that we were looking at. And at some point we were starting to generalize it to other contexts, and we had the good idea of asking a group theorist about it, you know, what he thought of that, Douglas Macpherson. And he said, well, maybe you should look at the papers of Goerge Willis. And we did. And indeed, I mean, the results that he was looking at, I mean, in particular, these tidy subgroups, well, in the case of difference fields of characteristic zero, this was exactly what we needed. And in fact, looking at his paper allowed us to generalize our result and to make it stronger. Going to the positive characteristic case meant that we had to change the proof, but well, so we managed. So these are the things I'm going to tell you about. So first of all, what is a difference field? A difference field, it's just a commutative field with a distinguished automorphism, which I denote by sigma. So they exist in the world. They were first considered in analysis, and actually the name comes from analysis because you have, for instance, equation like y of t plus 1 minus t, y of t equals g of t. I mean, such equations. So you want to find a function y which satisfies such an equation. So, right. So usually sorry, I see a typo here. So it's not an automorphism, it should be an endomorphism, which sometimes is on 2. Sorry about that. Which means that there are always typos. So I don't know, I might be able to do something about it, but no, I'm not able to do so. Okay, I don't master this thing yet. Anyway, automorphism or endomorphism, it doesn't really matter. What happens is that if you have a field with a different...
Sorry, Zoe, to interrupt. I can see a copy of the paper. Should we be seeing something else?
There is no paper.
Ah, I can see a copy of your paper, an invariant for difference field extensions.
That's interesting. So, I mean, it's not showing the right thing. Why should you see my... So what exactly are you seeing here? Are you seeing a slide which is number 3 and says definition?
No, I'm not seeing that at all. What can other people see?
Oh, this is annoying.
Yeah, I think it's
Yeah.
it's your PDF viewer, which has a couple of PDFs open inside it, and the paper is the
Sorry.
one that's
Okay,
open.
let me stop share and try to share something else. No, I think I know what it is. Yes, sorry. I didn't share the right thing. Wow. Sorry, absolutely sorry. So do you see it here now?
Yes,
Oh, yes.
thank you.
I'm sorry. No, I just did the wrong file. Okay, so let me go back then. So these are the references of the two papers. So my paper with Hrushovski and the paper of Goerge Willis, whose results helped us to improve our results. Okay, I should mention that in the case, again, I repeat myself, in the case of characteristic 0, our result follows from his. In the case of characteristic P, positive, some more work needs to be done. So a difference field is a commutative field with a distinguished endomorphism, which I denote by sigma. If it's on 2, then it's called inversive. So whether it's onto or not is not very important, because there is a sort of unique smallest inversive difference field containing a given difference field. It's called the inversive closure, and it is unique up to isomorphism over the difference field, okay? It's just you take a directed limit of various fields. So the examples, the typical example which come from analysis are C of t, where sigma is the identity on C and sends t to t+1, or sigma of t equals qt, where q is a non-zero element of C. And these are very much studied in analysis. You want to, you have a system of difference equation, in other words, things polynomial equation in sigma in y, sigma of y, sigma square of y, and so on and so on. And you want to find some function of t which will satisfy this difference equation. So typically you work actually in larger fields than C of t, let's say in the field of meromorphic functions over C or things like that, okay? Right, but then you also have more algebraic examples. For instance, if you look at, say you take your favorite field K, you have sigma the identity on it, and you take an indeterminate X, and now you're going to say that sigma of X square should be equal to X cubed. Now you see that this means that neither X nor sigma of X is in the field generated by the other one. Okay? So you get a field which is sort of strange. I mean, it's not, when you start closing under sigma, right? I mean, you have a unique way of closing under sigma. You will have that sigma square of X square is equal to sigma of X cube, things like that, right? So you will have a field which is not finitely generated over your base field, okay? So these things are a bit complicated. And indeed, and also if you want to close under inverse, then you will have also an extension. So you notice that starting with X, if you start closing under sigma, you will get extensions of degree 2 at each stage, right? Closing under sigma inverse, you will get extensions of degree 3. Okay, a tower of extensions of degree 3. Is that okay? So this is a typical example of equations we will be dealing with. All right. So I'll introduce first some notation. I mean, K-alg is the algebraic closure of K. Ks, it's separable closure. G of K is the absolute Galois group of K. In other words, you can think of it either as the automorphism group of K algebra K, or more precisely, the Galois group of Ks over K. So I mean, it acts on the separable closure and of course also on the algebraic closure, the extension to the algebraic closure from the separable closure being unique. So this is a profinite group. This is the inverse limit of Gal of L over K, where L runs over all finite Galois extensions of K. Finite Galois, that means separable, and that it's generated by an element and it contains an element which satisfies a certain polynomial equation over K, and all the conjugates of that element are in the Galois extension L. So as with finite Galois theory, you have a duality between closed subgroups of G of K and separately algebraic extensions of K. The duality is given by, to a closed subgroup H of G of K, you associate the subfield of Ks, which is fixed by that closed subgroup H, and vice versa. Giving an algebraic extension of K or separable extension of K, you can look at the set of elements of G of K, which are the identity on that algebraic extension. All right. So what I'm interested in is particular difference fields, right? So let's work inside a big one, U, and we take a different subfield. We take K, and we take a tuple of elements of U. I want to denote by K of A sigma the difference field generated by A over K, meaning K of A, sigma square of A, sigma cube of A, and so on and so on. If K is inversive, in other words, if sigma of K equals K, we can also consider the sigma inverse difference field generated by A over K. In other words, K of A, sigma inverse of A, sigma square, sigma minus 2 of A, and so on. And finally, the inversive difference field generated by A. Okay, so as I said before, these fields are usually not finitely generated. They are finitely generated in very particular case, but not all the time. So I will be dealing with degrees of extensions, and typically I'm interested in the various degrees of various approximation of the difference field generated by A. So I'm going to use an abbreviation. I'm going to denote by mu K of A over B the degree of the extension K of AB over K of B, if it is finite, and plus infinity otherwise. In our case, we will always look at things which are finite, so we shouldn't worry about it. Yes, I guess I should mention, you know, among difference fields, for instance, you could have that A, sigma of A, sigma square of A, sigma cube of A, and so on, satisfy absolutely no polynomial equations with coefficients in K, in which case you would say that the elements of the tuple A are what's called transformally transcendental over K. I mean, you have a notion of transformally transcendence, transcendence associated to the operator sigma. Those things, well, they don't, I mean, you don't have much to say about these things. I mean, the interesting cases are really when the difference field generated by A over K has finite transcendence degree over K. That's when things happen, okay? Right. And you notice that if it has, yeah, right, well, okay. Let me continue. Are there questions at the moment? I mean, I'll go back to the notation, don't worry. I mean, okay. So there are two invariants, which are invariants of the difference field equation K of A sigma over K. So you look at the the degree of k of a sigma of a, etc., sigma n plus 1 of a, over k of a, etc., sigma n of a. In other words, I'm looking at what is the degree of the extension obtained by adding sigma n plus 1 of a to k of a dot 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 sigma n of a. All right. So if at some point this degree is finite, then it can, if some parameter is finite, then it's going to decrease at its stage, okay? Because if sigma n of a, if sigma n plus 1 satisfies a certain equation, f of a dot 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 sigma n of a, then sigma n plus 2 of a will satisfy the same equation, but to which you have applied sigma, all right? Now it could be that the f that was witnessing the algebraicity of sigma n plus 1 of a over the previous one was irreducible, but then when you go one step further, that it becomes reducible and then the degree drops, okay? So anyway, so either it's always infinity because the tuple A contains an element which is transformally transcendental over K, or else it is finite and exists, okay? And the point is that one shows fairly easily that it does not depend on the generator you choose for your extension K of A sigma over K. It just depends on the extension, all right? One can also define what's called the inverse limit degree, and intuitively it's the same invariant but for sigma inverse, except that, well, if your field K is not closed under sigma inverse, then it doesn't quite make sense. So you need to do a bit of a trick, but it's defined in the same way. And it turns out that actually, so as I said, both these things depend on the extension K of A sigma over K. Their quotient depends on the extension K of A sigma alg over K alg, all right? Okay, right. There are multiplicatives in tower. Of importance are those, for instance, where the limit degree is equal to 1, all right? Then what does it mean? Limit degree equals to 1. This means that after a while, sigma n of A belongs to the field generated by the previous one, by A, sigma of A, etc., sigma n minus 1 of A. So in a sense, you are in one of the examples of, you have they are easier to understand. So at least K of A sigma will be finitely generated, but it might be that the inversive closure of K of A sigma is not finitely generated over K, even if K is inversive, all right? So for example, if you look at, you define sigma on K of X by setting sigma of X equals X squared plus 1. So you see it defines an endomorphism of K of X, but that endomorphism is not onto because K of sigma of X is of co-index 2 inside K of X, all right? One important tool is, so if you go sufficiently far, and if you go at the point where the degree of the extension sigma n plus 1 of A over the previous one stabilizes, and you replace A by the tuple A dot 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 sigma n of A, then you get that, so let's call this tuple B, then you get that the degree of K of B, sigma of B over K of B is going to be equal to the limit degree of A over K. And it's quite convenient to make that assumption. So at the cost of replacing A by a concatenation of some transforms of A, you can always assume that you are in that situation. In other words, the degree of sigma of A over K of A is equal to the limit degree of A over K. What happens then, assuming that the field K is inversive, the fields K of A sigma and K of A sigma inverse are linearly disjoint over K of A. This is fairly easy to prove. It's just because the degree of, let's say, sigma square of A over K of A sigma of A is not going to drop if you add to K of A sigma of A, K of sigma inverse of A, and so on and so on. Because we saw that this is the minimum value it can attain. So this is fairly convenient, it's fairly important. And one of the consequences is that if you take three integers, positive or negative, whatever, then if you look at the degree of the extension obtained by adding sigma j of A to K of sigma I of A, sigma K of A, right? Then it's the same as the degree of the extension obtained by adding sigma j of A to the extension where you add to K all sigma L of A with L less than or equal to I, and all sigma L of A with L greater than or equal to K. So this is quite a important tool, because then you see that, for instance, if you replace I by I minus 1 and K by K plus 1, then this multiplicity might increase slightly, okay? Right, okay. Might increase even very much, one doesn't know. All right. So what we are interested in is the following number, which we call the distant degree of A over K. So we saw that these sigma n of A, they have a certain degree over K of A, and we take the limit as n goes to infinity of this number of the degree of sigma n of A over K of A to the 1 over n. So the nth root of the degree of sigma n of A over K of A. All right, and the limit. It can happen that it's the limit degree of A over K. For instance, in the 3 examples I mentioned, this is the case. All right, when we had the sigma of x square equals x cube, was it sigma of x square equals x cube? Yes, the distant degree was equal to 2. It can happen, right. And then what happens is that actually, if you look at K of A sigma n of A, then all the intermediate transform of A are in the field generated by A and sigma n of A. Might not be as obvious as you say. I mean, you might have to think a bit about it in the example sigma of x squared equals x cubed, but you'll see that it's true. There is a similar definition for the inverse distance degree. And again, well, actually you have that the quotient of the limit degree, the limit degree over the inverse limit degree is equal to the quotient of the distant degree by the inverse distant degree. That's not hard to show. And also you can show that if B is algebraic over K of A, then the distance degree of B over K is less than or equal to the distance degree of A over K. And this means that actually the distance degree is an invariant of the extension K of A sigma alg over K. But it's not multiplicative in tower, which is unfortunate. Okay, you notice that, for instance, if A is in the algebraic closure of K, right? Then you will have that the degree of sigma n of A over K of A is bounded by the degree of sigma n of A over K. I mean, or by the degree of A over K. And so you see that in case A is algebraic over K, in fact, the distance degree is 0. All right. Is 1, I mean, is 1, sorry. Is 1. It's a constant to the 1 over n, so it's 1. Okay. So we wanted to study this, invariant. I mean, somehow, well, I guess one of the results we had was that in general, when the distance degree was equal to 1, meaning when the multiplicity, when the degree of sigma n of A over K of A is bounded, okay, independently on n, actually what you could find is that you could find a B inside the difference field generated by A, such that sigma of B is in K of B. All right. So that was quite, this was a result that we had, and we were wondering whether we could find something more general, but okay, we didn't manage to until we found Goerge's paper. And indeed, one of the things we wanted is this condition that sigma n of A, sigma n minus 1 of A is in the field generated by A and sigma n of A. This was the kind of, why doesn't it stop? Okay. This was the kind of condition we wanted. All right. So let me show you the main lemma, which is, okay. So we are in a setting where sigma of A is algebraic over K of A, and we have attained the limit degree. So in other words, the degree of K of sigma of A over K of A is equal to the limit degree. It cannot go down, okay? So as I said before, this means that the field K of A sigma and K of A sigma inverse are linearly disjoint over K of A, all right? And the main lemma says that if you look, remember, what we would like is that sigma of A is in the field generated by A and sigma L of A for L greater than 0. So what we have is that when L increases, the degree of sigma of A over that field, K of A sigma L of A, is increasing. However, it's of course going to be less than or equal to the limit degree of A over K, of course, because A is there, right? So it's an increasing sequence of numbers less than or equal to the limit degree of A over K. So this implies that it will stabilize at some point, all right? So let's suppose it stabilizes at L0 and let M be its value. Then actually you will see that we get a striking result. So you, first of all, you take the constant C, which is the multiplicity of sigma of A, etc., sigma L0 minus 1 of A over K of A, sigma L0 of A. In other words, I look at the extent, I look at K of A sigma L0 of A, and then I look at the extension obtained by putting all the transforms between 0 and L0 of A, all right? What happens is that one can show that if you increase so I'm sort of confused now, but okay. If you take J and L, which are greater than or equal to L0, and you look at the degree of the extension obtained by adding A to K of sigma minus J of A, sigma L of A, then you get some number which does not depend on L and J, it only depends on L0 in a sense. Well, this is actually not so surprising because what we saw before is that, I mean, in a sense, what one shows is that this number is the same as if you were adding sigma to the bottom field, sigma minus L0 of A and sigma L0 of A. That's what one shows, doesn't change. And with M as above, you get that the distance degree of A over K is the quotient of the limit degree of A over K by M. All right. So we get is, well, assuming one can find the L and the M, I mean the L0 and the M, you get a computation of what the distance degree should be. Okay, of course it's not, I have 10 minutes, 12 minutes left, is that it?
You can go up till 11 o'clock, I guess.
Okay, so 20 minutes then.
Oh yeah, you have about 15 minutes to allow for questions.
Okay, so from this one gets the following result. So assume that K is inversive, sigma A is algebraic over K of A, and actually I don't need the fact that the limit degree of sigma of A over A is equal to that the degree of sigma of A equals over A is equal to the limit degree, but doesn't matter. Then there is a C, however, there is a C in K over A sigma such that A is algebraic over K of C and the limit degree of C over K is equal to its distance degree, okay? So we, in a sense, solve the problem. As I said before, when the distance degree is equal to 1, we knew how to do it. Here, the improvement is obtained using inspiration from Willis's paper, is that we can do it in full generality. So I guess I'm going to give an idea of the proof, and it's for this proof to work that I need the fact that the degree of sigma of A over A is equal to the limit degree of A over K, otherwise it wouldn't work. So what we have, we look at the tuple A and we look at the field generated by all sigma I of A, where I is either less than minus L0 or greater than less than L0, okay? Where L0 was given by the previous lemma. So here I have a field, right? I have a tuple A, which is algebraic over that field. So I look at its algebraic lotus. In other words, at all the equations with coefficient in that field, which I'm going to call, I don't know, L, why not L, and which are satisfied by the tuple A, all right? So I'm going to get this algebraic locus V. So it lives in a certain affine space, but it's a finite collection of points, right? That doesn't matter. it has a smallest field of definition, which is unique, all right? I call this field of definition little k. By what we saw, so it's the smallest subfield of this big K of sigma I of A, right? Such that the degree of K of little k of A over K is equal to the degree of the extension obtained by adding A to the big field, all right? Now, by two of the main lemma, we know that if instead of looking at modulus of I greater than or equal to L0, we look at modulus of I greater than or equal to some bigger L, right? I'm going to get that the degree of the extension obtained by adding A hasn't changed. So this means that actually this little k will be inside that field. All right? Sorry, it will be inside the field K of sigma minus J of A, sigma L of A, as soon as J and L are greater than or equal to L0. Okay? So in other words, it's going to be in each of those fields, because each of those fields are going to contain things which go to minus infinity and plus infinity. So it's going to be in the intersection, all right? So K is contained in the intersection of, it's contained in this field F. But on the other hand, we see that sigma of F is equal to F. So therefore, also all the transforms of K are contained inside that F, all right? Little k is finitely generated over big K. Because when you look at the field of definition of an algebraic set, it's always finitely generated as a field, all right? And well, one can then compute using the fact that the degree, a certain degree was minimum and so on, maximum, yeah? You can then compute the fact that C is in the field generated by over K by sigma minus L of C and sigma L of C. And then eventually that sigma of C is equal to K of C, sigma L of C for all L greater than 0, which is exactly what we wanted. So you see, you have a sort of explicit description of this C. I mean, well, explicit up to, generated the same extension of K, but it's sort of nice. We were happy. Okay. So let me show you some of the properties. So one can characterize the C. So I have my A, which is such that sigma of A is algebraic over K of A and of same degree over K of A as the limit degree of A over K. C constructed as before. Then one can characterize those elements which are equi-algebraic with A over K and have as limit degree the distance degree as those which have which have smallest possible limit degree over K, modulo the constraint of being equi-algebraic with A over K. And in fact, if they satisfy the condition of that their limit degree is equal to their degree over of the degree of sigma of d over k of d, then one has the equivalent statement for sigma inverse. Okay. And it satisfies the same, it satisfies the same conditions as C satisfied. One can also find a, well, okay, 2 is sort of obvious. Less obvious is 3, I mean, now it is obvious, right? That the distance degree of A over K divides LD over K. This comes from the fact, now it's obvious because it comes from the fact that K of C sigma is a sub-extension of K of A sigma, and we saw that the limit degree is multiplicative in power. So this is multiplicative in power. So this is sort of obvious. And well, so then there are other properties. Let me go to Willis's talk, to Willis's proof. So let me remind you how it works. You have G totally disconnected local compact group with a continuous automorphism alpha. You take an open compact subgroup of G. You define U plus equals the intersection of the alpha n of U for n greater than or equal to 0. U minus the intersection of the alpha minus n of U. And you say that U is tidy for alpha if it satisfies that U is equal to U plus U minus is equal to U minus U plus. In other words, the group generated by U plus and U minus, and so on. And the second condition is that the union of the alpha n of U plus and the union of the alpha minus n of U minus are closed in U. And then one defines something called the scale function, and it's an invariant of alpha, in fact. So the theorem is that given alpha and G, then G has an open subgroup U, which is tidy for alpha. All right. So let me translate and let me show you how this gives our result in the case of the characteristic 0. Right. So we have, let's start again with the same setting. K equals sigma of K, A finite tuple in U, L equals the algebraic closure of K of A. And well, I guess I don't need A in U, I just eat an A in a field, something. And we look at G equals the automorphism group of L over K, and V equals automorphism of L over K over A. Now, I guess I need A to be in U, so, and I assume that sigma of A belongs to K of A, to L, right? That's what I need, sorry. Now, because L has finite transcendence degree over K, or actually even in general, G is locally compact, and V is an open subgroup which is profinite. V is, yeah, it's the automorphism group of the algebraic closure of K of A over K of A. The action of sigma on L, which is fixed because L is contained in U, induces a continuous action alpha on G obtained by sending tau to sigma inverse. And this maps V to the automorphism group of L over K of sigma of A. Okay. So in other words, it sends the absolute Goerge group of K of A to the absolute Goerge group of K of sigma of A. And if you look at what V plus and V minus are, they are simply, because of the Galois duality, they are simply the V plus is the absolute Galois group of K of A sigma, and V minus is the absolute Galois group of K of A sigma inverse. All right. So the first condition of tidiness will exactly correspond to, in fact, that K of A sigma and K of A sigma inverse are linearly disjoint over K of A. In other words, that the degree of sigma of A over K of A is equal to the limit degree of A over K. Condition T2, which was, this is not what I should do, which was that if you look at all the union of all the transforms of U plus, it's closed in U, and all the negative transforms of U minus are closed in U. Then, well, this is not so clear what it is, because union corresponds to intersection by duality, right? So actually it does give a hint of why our proof worked. But given that T1 holds, it actually implies that alpha of U contains U intersected alpha L of U for every L greater than 0, which corresponds exactly to sigma A belongs to K of A sigma L of A. So in other words, if we have a tidy subgroup, if V has a tidy subgroup, if G has a tidy subgroup, this will, the fixed field by that tidy subgroup will be of the form K of something, will be a form, yes, with limit degree equal to the distant degree of A over K. And this is what we want. All right. So what does it give? It gives an alternate definition of the scale of alpha, right? But this is not very new because it was also, it had been previously observed by Rookie-Muller. Right. And I guess it also gives another characterization of tidiness, which is that if U satisfies T1 and W is a compact open subgroup of G which contains alpha minus L of U intersected alpha L of U for all L sufficiently big, then W is tidy. All right. So I guess, well, we wrote this paper, and I mean, we were amused at looking at a dictionary, you know, between the two situations. So you took a theorem which looked obvious in one context, and you translated it into the other context, and you found that it was a bit less obvious. And we had a good time, I mean, doing this. I mean, it was a curiosity, it was pleasant. So we were able to give a model theory interpretation of this. I mean, in other words, when you have a certain group G like this, so you can associate to such a G and alpha and a compact subgroup with trivial normalizer. I mean, with trivial normal course, sorry, you can associate a what we call the strongly minimal structure, and in such a way that this is just a translation to that setting of this is the G is going to be the automorphism group of a certain structure, and so on and so on. So this was just a curiosity for us. I don't think it has much interest for you. And I guess I'm going to stop. Thank you. maybe you want to see the example where it's not multiplicative in tower.
My question was going to be, could you show us slide 10, please? My first question.
Which slide?
Slide 10.
Slide 10.
I think that's the example.
That's the example. Okay, it's a stupid example. I mean, but it shows that there is something definitely wrong. You see, so I have algebraically closed K of characteristic 0 with an automorphism or not, it doesn't matter. It could be the identity if you want. You take a generic solution of sigma of A square equals A square plus 1. Okay, so in other words, you take a transcendental A over K, and then you start solving the equation of sigma of A square equals A square plus 1, and so on and so on. So you get a difference field like this. And then you are going to take a solution of sigma of B equals B plus A. I mean, these things can be just constructed, you know, by hand. You take K, I mean, you take the difference polynomial ring in 2 variables and you quotient it by the difference ideal generated by those things, okay? By sigma of X square equals X square plus 1 and sigma of Y equals X plus Y, okay? If you want, you can look at the reflexive difference ideal generated by this and so on. So one can compute, of course, that dd of A over K is the same as dd of A square over K, and it's equal to 1, because you see A square, I'm just adding 1 to it. I mean, so it's an automorphism of K of A square, right? So the distance degree is equal to 1. For the same reason, the distance degree of B over K of A sigma is equal to 1, because sigma defines an automorphism of K of A sigma of B, right? Right. However, if you start computing the limit degree of the limit degree of AB over K is equal to 2. That's because the limit degree of A over K is equal to 2. All right, good. But if L is greater than 0, so we are interested in the distance degree of AB over K, right? This is going to be the same as the distance degree of A square B over K, right? The distance degree of A square B over K, this has to do with the degree of the extension sigma L of A square, sigma L of B over A square B, right? And when you look at the subfield, which is, so sigma L of A square, it belongs to A square, so it doesn't count. But sigma L of B minus, because sigma L of A does not belong to K of A, it will follow that, in fact, if you look at the equation at this extension, so K of A square, sigma L of B minus B, you see that it is an extension of degree 2 to the L of K of A square. So you see that the degree grows, okay? And in fact, so you obtain that the distance degree of AB over K is equal to 2. In fact, I mean, it's not particular to that example. It's just the fact that my A was not while A square had limit degree 1, A did not. That was the problem. Okay. So okay. That was unfortunate. So I see that there are people chatting, but I mean, aha.
Yeah, there were some clarifying questions in the chat, but they were not completely related to the talk. It was about Willis theory, so I felt not appropriate. Also, Colin was doing a good job of answering them in the chat.
Yeah, because, yeah, of course, it's these results, right? So, right.
Do we have any other questions for Zoe?
Yeah, I'll ask another question. Were there any particular fields and endomorphisms or automorphisms that were of particular interest to you? Or was it just a general result you're interested
No,
in?
it's, I mean, we really look at them much in general. I mean, okay, one of the results that I guess there was the question of the relation between the A and the C. Well, let's say that we thought it was somehow, you know, when the limit degree is bigger than the distance degree, that means that there is some noise, in a sense, in the extension K of A sigma, and sort of we wanted to eliminate that noise. We haven't found any application. I mean, we thought that there would be some, but somehow we stopped working on concrete computational problems, and so we didn't apply it to anything. But I mean, we have hope that it can be applied for certain things, you see. I mean, for instance, one of the things that we have, so we have several different behavior of difference equation. And for instance, one of the bad behavior is when it's strongly related to the fixed field, okay? So, of course, I mean, this is something that we already had in a sense, but one can imagine that there are other situations where it can come in handy. And what's happening is that if you have a difference equation which is strongly related to a fixed field, in fact, you can in the sense that it's at the cost of enlarging the set of parameters, it's sort of generically in generic finite to finite correspondence with a set defined in the fixed field. Well, actually, you can make this correspondence more precise and really get it to, at the cost of going to of a projecting to get it to be living really in the fixed field, stuff like that. So, I mean, it can allow us to sort of specialize certain sets defined by difference equations to sets which might be more tractable. That's what we were hoping. But well, you know, the thing is that when you work in full generality, I mean, problems are hard to, I mean, it's, there are many problems, right? That means you don't know what to attack exactly.
Yeah. So this is for sigma inversive. Is that a necessary assumption for you?
No, not necessarily. I mean, well, I mean, you can always extend it to the, yeah, I guess, right. Yes, you can always make it inversive in a sense, but yeah.
Oh,
but I mean, in the same way as your automorphism is an automorphism. I mean, it's,
yes, the results on automorphisms of totally disconnected groups can be extended to endomorphisms.
You see, what's happening is that from the moment that this C is in the, wait, did I get, wait, what did I show? We should get rid of the chat. Yes, okay, right. Here, a priori, the way I described it, it's not completely sure that it is in K of A sigma. It could be in K of A sigma plus minus 1, right? But nevertheless, once you have such a thing, you know, if you apply sufficiently many transforms of C, you can get it to land in K of A sigma, all right? I mean, that's not, to be in K of A sigma or in K of A sigma plus minus 1 is about the same thing. I mean, you just need to apply. Is that okay?
Yeah, I guess I'm just wondering whether the results about endomorphisms of TDLC groups
that's something, yeah, right. I guess we are very much using the fact that, but it probably should be true in your case too, no?
What should?
That you have a sort of inversive closure. You see, because if your endomorphism is not onto, then you are sort of trying to, so you have G and you have alpha of G, right? But you can copy this to produce something which is alpha inverse of G, G. And so on and so on. You know, that's the way they, and you still will maintain the local compactness. You see what I'm saying?
Yes. So maybe, so in the case of endomorphisms of groups, I think there's an invariant sort of subquotient of the group in which your endomorphism becomes an automorphism. So maybe that's the corresponding statement to your closure.
Yeah, I don't know.
Oh, that have to think about that one. Also, what if have you thought about if you have more than one endomorphism, but several commuting ones?
The problem with several commuting ones, okay, one of the things which makes things work here also is that you see every automorphism of a field extends to its algebraic closure. But now if you have two commuting automorphisms of a field, they extend to the algebraic closure, but not to commuting ones in general. You see, I mean, for instance, if you look at Q, well, it doesn't have many commuting automorphism. Q-alg, sorry. It doesn't have many commuting automorphism because the only abelian subgroup is, if I remember well, it's Z hat. I mean, yes. Okay, no, I'm not saying it right. I mean, it doesn't have any abelian subgroup isomorphic to Z hat cross Z hat. Okay? Or to ZP cross ZP or something like that. And for instance, if you look at the Goerge group of the absolute Goerge group of C of T, you know it's free for finite, so it has same thing. It doesn't have, I mean, the abelian. So that's the problem. It doesn't have. There aren't many fields with. I mean, fields with two commuting automorphism, as soon as you want it to be reasonably rich, it's not going to be algebraically closed. Reasonably rich in terms of solving difference equations, okay, systems of difference equations, it will not be algebraically closed. That's what's happening.
Right. Okay.
And I think that might be a problem. And also, you know, I mean, with two automorphisms, so of course you have more invariance, right? I mean, so here, you know, you are either transformally transcendental or transformally algebraic when you are an element, okay? If you have two automorphisms, then, well, you might be, I mean, you might have a mixture of the two, right?
Mm-hmm.
So it's more complicated.
Ah. All right, okay. I had a comment too. You mentioned the model theoretic description of TDLC groups that you have at the end of your paper.
Yes.
And you thought it might not be interesting for us, but maybe it is, because it looked to me a bit like the representation of a group as acting on its Cayley-Arbel's graph. That's also a sort of generic representation of the group, of the group, general representation of these groups. So, and that is useful. So it may be that this model theoretic description also has its uses.
Yeah, but well, okay. So, no, I thought it was you know, I thought it was sort of what do you call it? It was too much designed to work. You see what I mean? But anyway. Yeah. Because you see this structure that we put on, actually I did write the slide, I think. So I can show it to you. So this is the following construction. You have G totally disconnected local, and you assume that O is an open compact subgroup which does not contain any normal subgroup of G. So you can always achieve this by quotiented by the intersection of the conjugates of O, right? Now you look at the quotient space X, which is G mod O, and you put some n-ary relations coming from the action of G on finite tuples in X. And you look, so you add these relations, and you look at the structure which is obtained by taking X and all these relations. So it's so the language is sort of huge, right? Because you are looking at all the orbits, all the finite orbits of G, right? All the orbits of finite tuples of elements of X, okay? So it's huge, this thing. I mean, it's, and you look at the, so this M will correspond to our L over K, you see, to our extension L of K. And then if you look at O bar, which is the image of O in X, so O bar, O, remember it was compact, so the image of O in X is going to be compact. And then you see that the map, so G acts naturally on M, you know, by, because G acts on X. And of course it's surjective, and because we did exactly what was needed for it to be surjective, I mean, and it sent O onto the elements of M which fix O bar. So this is going to correspond to the absolute Galois group of K of A, you see. That's how I'm translating it.
By the way, we do have a comment in the chat from William that maybe the inversive closure in groups could be the projective limit of the system. And there's G, the maps between them where all arrows are the endomorphism under consideration. Or
Yeah, I
is
guess
that what
that's
George
what
meant?
George meant, yes. Whereas I meant the
Yes.
I meant the other way around. I meant the inductive limits of things.
Yeah, maybe that makes more sense indeed to take the direct system then, because then G is embedded in it. Yeah, I see. Okay.
No, I mean, it's true that in a sense, you know, if you want to apply duality, then a larger structure would correspond to a smaller group, right?
Nice. Yeah.
Yeah.
But on the other hand, well, I don't know. Yeah, I don't know.
I think I need to think carefully about these things. Take a bit longer.
Anyway, this is very much non-symmetric. I'm sorry. But I haven't worked on this for a while. It was interesting to get back into it.
Mm-hmm.
Well, do we have any further questions for Zoe? Oh, seems that not straight away. I guess if people are willing, we can still have a bit of a chat after the seminar. So let's thank our speaker one more time for the talk. Yeah,
Thank you.
Nice. And hopefully let's see everyone next time.